Okay, as I was saying last time before the break, we were going to define a special subgroup now. We even got some of my notes here. I won't erase this just yet from the previous time, but what we define is given any group G, we define the center of G to be the set so let's look at what the set is. It's all elements A and G such that AX equals XA for every X and G. Let's just look at that. What we have there is we have the center would be it's a set. So we take elements of G. What properties do these elements of G have to have? G have to commute with all the elements of G. So the quantifier is on this X here. This is a fixed G. It's those G's such that X commutes with, it's those A's such that X commute, all the X's in the group commute with it. And we denote the center of G by Z of G. And sometimes if we're only talking about one group, we may just call the center Z. So theorem, given a group G, Z of G, the center is a subgroup. Okay, so let's going to show that. Let's try to do a subgroup test. We're actually going to use subgroup test 1, the two-step subgroup test. So certainly, the center is a subset of G, because every A, in addition to meeting these other properties, you have to be in the group G. Now, for all X in G, XE is equal to EX that's because both equal to X. So what does that tell us? That tells us so the identity is in the center of G, and so the center is not empty because it's at least got the identity in there. So you might remember both subgroup test 1 and subgroup test 2 start out with this assumption that you've got a subset that's non-empty. So we have that. We will use subgroup test 1. And what I call subgroup test 1 let's take two elements in the center. Then for all X and G, what do we have? We have, if we look at A times B times X, we can scoot that over. That's equal to A times BX. We have associativity. But then B is in the center, so that means B B commutes with X, so BX is XB, but we have associativity again. But A is also in the center, so A commutes with X, so AX is equal to XA. And yet again, we have associativity. So XA parentheses B is the same as X parentheses AB. So thus, for all X in G, ABX equals XAB. So I erase it here. What does that mean? That means exactly that AB is in the center, right? Because it commutes with every X in the group, G. Now the next step, take any A in the center. Then AX equals XA. So let's multiply by A inverse. A inverse AX on both sides, A inverse is equal to A inverse XA, A inverse. And we have some associativity, so that would give us A inverse AX A equals, not A inverse AX, A inverse AX, A inverse. And then the right-hand side would be A inverse, we'll use associativity there as well. A inverse X, parentheses, A inverse. So here. So what does that happen? Well, A inverse A is E. So we'd have that. But A inverse is also E, which would mean the right-hand side would be that. But E is both a left and right identity. So this is X, so that's X A inverse X. And what was special about X? Nothing. So this holds for any X in G. That is, A inverse, basically, A inverse is in the center of G. So we've shown the second step, right? If we take any A in the center of G, its inverse, in fact, has to be in the center. So by subgroup test, the center is a subgroup of G. And the last statement we want to make is just sort of a corollary of this, is that the center is an abelian group. Let me erase this top statement, maybe state a new one, give you time to look a little bit more at that proof. So corollary, given any group G, Z of G is an abelian group. Well, we have just shown that it's a subgroup, so a subgroup is a group. We have just shown Z of G is a group. Take any two elements, A and B, in the center. Since, for instance, AX equals XA for any X in G, and B is an element of the center, which is contained in G, we have in particular that AB equals BA, and Z of G is abelian. That's required. So we'll close with this remark. G is an abelian group if and only if the center of G is the entire group. So in some cases, the size of the center, the bigger the center is, the closer the group is to being commutative, abelian, which means the multiplication is commutative. So if the center is all of the group, then that means, well, this is an abelian group, so this would have to be. Okay, so we'll take a break now. We'll continue moving on to the subgroups, and we'll even look at a special type of subgroup called a cyclic subgroup.